Thank you. It's a huge pleasure to be here in the physical sense of the word, as well as in the intellectual sense of the word. What I want to do today is dive in a very precise case study that I think will illustrate a couple of general points that can feed the discussion for those 2 days. And it starts with the remark that if you look languages after languages, natural languages after natural languages, you don't find a word that means green or red. There are restrictions on the kind of color words that you find in natural languages. And there is a nice generalization of this fact, which imports from what we know about psychophysics of colors. And that says that when you have a color word, it has to cover a connected space of our perceptual space of color words. So the perceptual space of color words is typically represented like this as a cone, and red and green are in different parts of this cone. Therefore, you're not going to find a word that encompasses those two without encompassing other colors, at least, those that are in between. Now, this can be extended to other kinds of words. So for instance, you don't find easily a word that means carrot or banana and nothing else. That would apply to only those two kinds of vegetables. And it looks like the same generalization. It looks as if there was a word like this that would refer to those two kinds of objects, it would also refer to all the objects that you can think about as being in between those two vegetables. Problem is, in that case, it's not as clear what it means to be in between a carrot and a banana. We don't have all the psychophysics behind it, so we need to apply other means to investigate that. Fortunately, people have done that. So in this study, in particular by Su and Tannenbaum, what they've done is that prior to looking at what word means, they would ask participants to give their assessments about the similarity between pairs of objects, okay? So is a carrot close to a banana? To what extent is it? And from these judgments, they would infer the topology of the objects, of the space of objects. Next thing they would do is ask people to learn words that would apply to subsets of these objects. So maybe not, yeah, may not, let's suppose it includes carrots and bananas. And then they would say, look, this new word, blicket, applies to those objects. Now, what other objects do you think blicket applies to? And what they found is exactly the generalization that I mentioned before. It is when the space they've gathered about these objects say that an object is between two examples of a blicket, that they think the blicket also applies to this word. Okay, so very much fulfilling the connectedness property of nouns that I described before. And now with a concrete notion of what it means to be in between, just like in the case of colors. There are two ways to think about those kinds of generalizations. One is to say, well, we partition the world around us in connected classes, right? Those classes around the colors or around the objects. And therefore, the words that we're going to come up with to talk about the world around us are going to be connected because it's the convenient thing to do. It's the thing we're interested in the first place. There's also the other way. We use connected words to describe the world around us. And therefore, there might be reasons to see the world through this filter and see the world as made of classes of objects. There are reasons to think that it's not the linguistic facts that drive the way we're going to look at the world in this particular case. I'm not saying this is not the case in other places. And the reason is a very striking one. The argument is rather strong. It's just the fact that animals would show the same connectedness effect about how they classify the world around them. So if you ask animals to go into classification tasks between sets of objects, the task will be much easier if the classes they have to discover are connected in the first place. Connected in one sense, in the human sense, okay? In the sense of what you get if you look at how humans categorize the world around them. Okay, so that's about connectedness for color words, and then we talked about concrete nouns. The question I want to ask now is, can we go one step further? And can we look at something that doesn't seem to fit in that domain, namely logical words or function words? Function words are interesting. They're also restricted. It's not the case that you can find just any kind of function word. Just like you don't find a word for red or green, you find a couple of words that are very common, and, all, some, none, in languages of the world, and some that are not at all common, if they exist at all. Things like not, both, none, or all. Those are perfectly conceivable, yet you don't find them. Connectedness is a good thing because it also helps us acquire new words. Because if we know that the word we're going to acquire is connected, then it's easier to guess what the end meaning of a new word is going to be. At least you know it's going to be connected, so that's the target. It gives you a target. Having a target for function words would also be helpful in that respect. Finally, when we look at function words, we move from looking at how we form concepts and classes into how we reason about them, how we form higher order concepts, how we become, a more intelligent species, if you like. So we're going to look at function words now. The framework I'm going to use is one in which we think about words as functions. Functions in the mathematical sense now, not in the sense of function words. So banana, for instance, you can think about it as taking an object and outputting true or false. Certainly this is something we can do, right? If I say banana and I show you an object, we're all capable of saying whether the banana applies to that object or not. There are several ways in which you can do it. You can have a probabilistic version of it. We're going to use the simplest symbolic version of it for the sake of simplicity and clarity. And so when we talked about banana, what we said basically was that this function had a shape like the one pictured here on the slide. Namely, it might be false for a while, on the x-axis. Then if it becomes true, it remains true for a while again, and then it becomes false and then stays false. It's not allowed to go up again. Whenever you have two cases of true, in between all the cases are also true. This is just the abstract version, the modeling of what I was saying about when I said that banana was a connected word. Now, interestingly, if you think about function words also as functions, you can apply exactly the same definition and just take a look at what it says and how it applies. We're going to look at quantifiers in particular. Quantifiers are things like all, some, none, here, many. And we're going to put them in sentences, in context in sentences like this. So consider an urn with balls in it, and then someone says about those balls, many are red. You can think about many as taking as input the set of balls and giving as output true or false. Simplifying a bit and reducing to one dimension because it's easier to represent on the slide, you can think about the x-axis here just as the number of red objects in the urn. And what many does as a function is that it's false for a while if you have 0, 1, 2 red balls. Then it becomes true and stays true. Now, there's this survey of quantifiers of the world, so words like many, by Keenan and Paperno, that as much as it's possible, exhaustively looked at quantifiers of natural languages. And we've we went back to this survey and looked at all the quantifiers that were listed in this survey. Among the most common ones were quantifiers like all, some, none, 5 or at least 5, less than 5. And all those expressions have the same kind of profile that we saw for many. Namely, they're false for a while and then they're true, or the other way around, they're true for a while and then they're false. And those are really common in linguistics. They have consequences. Monotonic quantifiers govern grammatical properties such as the felicity of polarity items that I think we're going to hear about tomorrow. And those are among the most frequent. Next were a more general class of quantifiers, namely those that follow the profile of connectedness. So certainly the monotonicity profile is a subcase of the connectedness profile. It does satisfy the fact that between two true objects, there's always an object that gives you true. In that case, not an object, a set of objects, but it's the same idea. And so next in line were quantifiers that were exactly connected without necessarily being monotonic. So things like 5, when it means exactly 5, so exactly 5 are red, is like that. It's false for a while, then you hit 5, it's true, and then it's false again, and then it stays false. Between 3 and 7, not a word here, a phrase, but still, if you look at phrases as well, they follow that pattern. Interestingly, if you just drop as much as you can from this phrase, and you just look at things like, back to the urn example, and you say things like 3, 7 are red, the way we interpret that, typically, is by closing the connectedness gap. That is, we understand 3, 7 as meaning roughly the same thing as between 3 and 7. There would be other ways to do that, but it seems that there is a strong bias to close the connectedness gap and get even this expression as having a connected meaning. And you can prove that there's a general connection between monotonicity, so this property that's central for lots of linguistic facts, and connectedness in this new sense, and this sense that has been imported from content words. Now, the kind of things that you rarely find in this survey of quantifiers across languages of the world are non-connected quantifiers. So what would be an example of a non-connected quantifier? It would be something like outside of 3 and 7 of the red balls are red. And in fact, it's not even clear that this phrase, is easy to manipulate, is grammatical, is felicitous, whichever way you want to put it. Certainly, you don't find it in the survey. Also, 3, 7 could have been interpreted like this. There was no reason why it would have been interpreted as connected, as opposed to, the opposite of connected. And it's not the case that it works like this. Instead, what you find is that whenever you have a quantifier or a phrase that's not connected, it's through the disjunction or that seems to be one of very, very few ways in which languages allow us to talk about non-connected things, even if there might be a bias against doing it. Languages do deliver the resources to do it, but it's only rare. Okay, so by doing this kind of abstraction words, we've been able to uncover a generalization about languages of the world that concerns color words, nouns, and now logical words, which presumably were in a different domain. And we can ask the same question about this generalization. Which way does it go? Is it the case that, for instance, we have connected function words that are going to lead us to reason, to extract patterns in a connected fashion? And I'll try to be more precise about what it means to reason in a connected fashion. And the way we're going to do that is in some sense related to the kind of things that Philippe Schlenker presented before. We're going to have people reason, but without words. And we'll see whether the reasoning tells us something. The kind of task we use is very much inspired by work by Feldman and Piantadosi about trying to to get people to reason about patterns and see what kind of primitive elements they use to reason about those patterns and how they put them together. The task was as follows. It had minimal instructions. People would see patterns of 5 circles with colors. I don't know if the colors are clear here. And they were just asked to say, in each case, whether some underlying rule that's untold is satisfied or not satisfied by the display. So you see a pattern and you say true or false. At first, all you can do is guess, and this is certainly what people did. But each time you answer, you get feedback. And through that feedback, you can gather information about what's the underlying rule and go for whatever you think is the appropriate answer with more and more good reasons. Luigi, what time do I go to? Because I started late. Okay. Underlyingly, what we had were rules that were either connected and monotonic in the sense of the quantifiers before, or just connected but not monotonic, or not connected at all. And we wanted to see whether there was a difference between those different cases. So I'll skip the details and jump to the results. We measured success by saying when is it that participants converge on particular responses and were correct in the sense of the underlying rule 100% of the time for more than X trials. And what happened is that with monotonic rules, they were the fastest, then non-connected rules, and then connected rules, those that satisfy the generalization we are after, so the more general case of monotonicity, and then not connected rules. So it does seem that this connectedness bias is there in reasoning, even independently of there being words. And so to the question I raised before, we might say, the direction is not from language to reasoning. But it's a kind of weak argument because we are talking about people that might have used their languages to do those tasks. And so we move to people who cannot use their languages to do those tasks, thanks to the collaboration with Joël Fagot in Aix-Marseille, who has a facility to test baboons. And here I want to make a methodological point about this experiment that I presented, and that was, as simple as possible. If you go back to it, it requires no language even to perform the experiment, even to read the instruction of the experiment. It's really minimal. So the effort of moving from language to no language has 2 consequences. One is that you may be able to make a claim outside of language. The other one is that you can apply the exact same paradigm to species without languages. And so we took advantage of this feature and ran similar tasks, now not with humans on the internet, but with baboons in this facility. So they had to classify patterns of colors within balls that would vary the amount of some particular color that you see in the ball. And there you can see how you can do connected patterns if in the target class you have a connected set of amounts or a non-connected pattern. We used a more stringent criterion for success of the baboons. They had to be correct for a number of trials for them to pass the task. And we measured how long it took them to pass the task, just as before for the adults. And as you can see, the graph is pretty much the same as the one before. Namely, you have baboons are much faster at finding out the monotonic rules and the connected rules than they are at finding out what is the non-connected rule. Okay? So now we have a stronger argument for saying that this connectedness constraints and generalization doesn't come from language, but comes from something that is a precursor of language, that might be before language, at least because you can find it in species without language. Another way to put it, which might be more provocative, is to say that if baboons were to develop a language with function words now, with their cognitive abilities, then they might develop the same function words as we do. So they might have a word for all and one for some and one for none, but it would be very surprising if they developed a word that we wouldn't have, something like none or all. Okay? As if the basis of our lexicons was completely independent of the language in the first place. It was some other kind of more primitive language, sometimes that people might call the language of thought, that could be present in the baboons as well, because they also have biases that we can identify very well. So what I've done so far is I showed you how to model a generalization that you observe in a particular corner of language, namely color words and nouns, and show that there was value in making the effort of abstracting away from the empirical facts and making it a mathematical claim and a symbolic claim about what this generalization is. Because then you can look at function words and you can look at other domains. And you can see first different kinds of evidence as to whether this generalization is going to hold behind the first cases that you've observed. So you can look at languages across the world and see whether it's a universal, absolute or relative universal. You can look at what happens without words, so in a learning kind of experiment, as I presented. And you can look even further into other species that do not have languages at all. Next thing is you can look at machines. Now, connecting more with the topic of this conference. And you can look at whether machines are going to behave like humans and like baboons and prefer connected patterns, infer them earlier, faster, more easily by whatever measure you can have, than non-connected patterns. The results are almost aligned. There is this study by Shane Steiner-Streckold and Jakub Szymanik, who looked at the extreme cases, namely the monotonic cases, which are connected, but even more than connected, and the not-connected cases, and they do find a difference. So the blue curve is the learning of the connected cases here, and it's faster, it ramps up very early, and the red cases are the non-connected cases. So what you observe here is basically the same pattern as for humans and baboons. Let's think about what we can learn from those facts. So from the baboons, it was easy to say that connectedness is not a consequence of language, because without language, you might have this bias for connectedness already. For neural networks, in this particular case, we might conclude from the fact that neural networks also show those biases, that connectedness is not a consequence of our interaction with the world, because neural networks do not interact with the world. So it's not about seeing balls that are more often than not in connected numbers or something like this that drives the fact that we have a bias for this. And in the work of Nicolas Guérin and the team, we found similar effects whereby we know that humans have biases for some relations. So humans prefer contact relations, as depicted here in B, than non-contact relation, even if they're kind of similar. It's about a ball being above a rectangle. And you can find that neural networks show the same kind of biases, even if they've never interacted with those kinds of objects. Now, there's another interpretation of those facts, of course, which is that the neural networks have been designed for a particular task, and by humans as well. So much so that our biases would be hardwired, would come up in those technologies just because it's the best thing you can do. And this can happen in several ways. One way in which it can happen is through an evolution-like kind of mechanisms. We're trying to find the best systems always, and the best systems are going to converge on those that have the same biases as the one we have. Another way is through some direct engineering. We know that those biases exist, therefore, let's go for it. Let's implement them. Let's bias our machines a priori to have them, as opposed to letting them figure it out. Luigi, can you tell me again about the time? 5 minutes, okay, good. So I want to explore and this can happen implicitly or explicitly. It can happen implicitly because we, as humans, have those biases, and whether or not we're conscious about those biases, we're going to implement them in the machines. We might implement them in the machines that we build. I want to connect to something, to the introduction by Stéphane Mala earlier today, who mentioned this idea about projecting the input space into some typology. That when we do that, the untold purpose is to find classes, natural classes in this new inferred topology that are connected, in essence. We're going to have a clustering algorithm that's going to come up with connected classes. And when doing that, we're actually making a design choice that maps well with the biases that humans turn out to have. I want here to, in the last couple of minutes I have, to just illustrate the kind of approach that we've taken to that problem. The classical way in which we train those the neural networks is by setting up with an architecture neurons that interact and are in particular functional relations. So you move from one neuron to another by applying some functions. And all you do during training, in most cases, is you change the weights. So you change the importance of the inputs. But a more flexible approach would be productive if we know the biases that we have. And in particular, we've looked at cases where we could do training by removing units, adding units, so changing the architecture, and changing the functions in the first place. Why changing the functions makes sense? Because we know that some functions are easier for humans to come up with, are more attractive, such that the overall architecture will encompass locally the biases that we know humans have, and hopefully globally would fit well as well in terms of generalization. To do so, what we did is that we implemented a training regime whereby the goal is not only to fit the data, but also to reflect about the architecture itself. And in the simplest version, you can think about as the architecture just trying to be small. And small in what metric? The typical metric is how long is the minimal description you can make of it. Another one is what are the functions that you're using? Are they functions that we think are biased in humans in the first place? If that's so, then we might give them an advantage at this stage as well. In doing that, the kind of results that you obtain is that you can solve classical tasks like addition, which is not that easy. It's a symbolic task that is not so easy to solve completely 100% with such kind of machines. You can solve tasks like inferring grammars of the kind A to the n, B to the n, and realizing that those sequences are correct, type 1 languages, and so on and so forth. And you can solve those tasks with neural nets that now look like the one there, and that has exactly 4 cells, because it tries to minimize itself at the same time as it tries to solve the task. And once you're there, you're not only able to solve the task, but you're also able to prove that you solved the task, not on a test set, but formally, because the network is manageable, and you achieve transparency of neural networks. The point I want to make there is that you can decide what are the primitives of those neural networks as well, and make them fit what we might infer are the primitive, the biases of humans as well. Okay, conclusions. What we've done is that we've looked at a very simple case in semantics, namely lexical semantics. But we've looked at it not in a completely narrow way, nonetheless, looking both at content words and function words at the same time, which is not necessarily the default. But doing that allowed us to infer a higher order kind of abstraction about languages and about humans and about reasonings in general, as well as baboons, as we saw. And so we tracked that abstract generalization cross-linguistically as well as extra-linguistically, so without words, in animals and in machines. This was collaborative work with Brian Bucola, Isabelle Dautriche, Joël Fagot, Nurlan, Ronnie Katzir, Maxime Côté, Nicolas Guérin, Ael Kelenek, And all those people here, wonderful people here, spread the whole spectrum of fields that we really want to collaborate, and that I think this symposium can help work together even more. Thank you very much.